In this session, I would like to demonstrate a small synthesis problem involving energy balance. By simulating, we are required to identify out of the given two options which one is better, and probably you need to analyze why a particular option is better than the other. So coming to the problem statement, ethyl benzene available at 77 degrees Fahrenheit and 14.757 psi is to be heated to 752 degrees Fahrenheit and 73.48 psi. There are two possible options which are suggested. The liquid ethyl benzene at the initial state is sent through a pump to increase the pressure to the desired value, followed by heating it to the required temperature. Whereas in the second option, the liquid ethyl benzene is first vaporized at constant pressure to an intermediate temperature and then compressed to the required pressure. So by simulating these two options, we will have to determine which one of these options is preferred and probably analyze why or what are your reasons for recommending out of the given two options a particular option. Now let us try to attempt at simulating this problem using Aspen. Now, the only component we are trying to handle in this problem is ethyl benzene. So, let me go to the next input screen, choose a property model, go to the next input screen, and go to simulation environment. Now, both the options I would like to demonstrate in the same example. So, I will be using a duplicator block. So in the first option, we are first of all compressing it to the required pressure using a pump, followed by heating it to the required temperature. As I am interested in only energy balance, I am not going into the design aspect, so I am selecting some simple models like heater. Whereas in the second option, we are trying to use, first of all, we are trying to vaporize by supplying heat to an intermediate temperature, then followed by compressing it to the required pressure, outlet pressure. So these are the models. So let me make the connectivities, provide the stream connections. You already saw the purpose of using a duplicator block. So whatever outputs that you will be able to draw from this duplicator block will have exactly the same information as its input. So S2 and S3 are going to be similar. Now from this, you can connect it to the heater followed by the output. Now here also, we can connect it to the compressor followed by the output. So having completed this flow sheet, now let us try to look at how to define the problem. So let me change the unit system because we are using temperatures and pressures. So 77 degrees Fahrenheit, the pressure is at 14.7. So let me, because it's only a synthesis problem, for comparison purpose, the flow rate, we can take any particular value. Let me assume the flow rate as 100 lb per hour. So we have defined stream 1, then go to the next. Duplicator, you don't have to give any information. So this is with respect to the pump. So the pressure is increased from 14.7 to 73.8. Right? So we have specified the pressure and we have completed the definition with respect to the pump. Go to the next. Now this is the heater in the first option. So this is the first option. This is the second option. So B3 is the heater available in the first option. So let us specify this. So we are going to heat the input to the final temperature of 752 degrees Fahrenheit. Maybe we can assume constant pressure or a pressure drop of 0 in this heater block. So we have specified the first one. Now coming to the second option, we are trying to heat it to an intermediate temperature or vaporize the input liquid ethyl benzene to some intermediate temperature, because when you compress, there is likely to be an increase in temperature. Finally, we would like to have the same 752 degrees Fahrenheit at the exit. So we may not be having any idea about this temperature. So let me presume some value, say 500 degrees Fahrenheit, for example. The pressure, this is a heater. Again, like what we have seen in the previous case, let me assume that there is no pressure drop in this heater block. See, remember, we don't know to what intermediate temperature we need to heat the liquid ethyl benzene and vaporize, such that when it is compressed to the required pressure, ultimately it should be at 752. We may not be able to know the temperature to start with, so I am presuming a value for this. Now go to the next input. So this is now being used as a compressor. You can choose isentropic. The discharge pressure once again is 73.48. So you can see all the required input is complete. So we should be in a position to run the problem. So we got to our results. Let us look at what is the output from the first option. So you know the liquid ethyl benzene is available at 14.7 psi and a temperature of 77 degrees Fahrenheit. We were able to increase both the temperature as well as the pressure to the required value. So we got to our objective. What is happening in the second case? So in the second case, we were able to get the required pressure of 73.48, but the output temperature is not at the required value of 752. So why is it? Because we assumed the temperature at the exit of this heater block as 500. So 500 inlet available at 14.7 degrees Fahrenheit when it is, 14.7 psia, when it is compressed to 73.48, the temperature was increasing from 500 to about 583. Now we should be able to finalize this temperature such that when it is compressed from 14.7 to the exit pressure of 73.48, we must be in a position to get the required outlet temperature of 752. So we can handle this by using maybe a design spec. I'll go to flow sheeting options, design spec, say new. Now define what is that we are interested in, the target temperature or outlet temperature. Let me name it as out T, the final temperature from the second option. So it's a stream variable. Again, stream variable. Stream is the last one coming out from this block. Then variable is temperature. Right? It is in degrees Fahrenheit. What is our requirement? So the outlet temperature should be at 752 degrees Fahrenheit. So give some tolerance. So spec is defined. What is that we are trying to vary? How did we get this as 583? By defining the outlet temperature from this block as 500. Right? Now we need to vary this outlet temperature such that the final temperature would be at 752 after compression. So the vary variable is a block variable. Block is B4 and the variable is temperature. So we know even 500 was not enough. So I would like to go up to 500 to 700. Anyway, suppose if it is at 700 after compression, it is likely to give the solution is expected to lie somewhere between 500 and 700. If you are not sure, you can even give a higher value. So we have completed the design spec information. So you can see what is going to happen. So as you can see from this example, what we are trying to do is we started with a temperature for this block as 500. After compression, we calculated the temperature of this exit stream. Compare this temperature that is calculated with what is required, that is 752. If it is not met, readjust this value. You know how this design spec is solved in Aspen using a secant method by default. So you can see this block, both B4 and B5. Why B4 and B5? See, the measured variable is here, the manipulated variable is in this block. So the design spec is involving both these blocks B4 and B5. So whatever are the blocks appearing between the measured variable and manipulated variable will be iterated because of this specification loop. So that's what exactly is happening here, because B4 and B5 are involved. So these blocks B4 and B5 are iterated maybe about 4 times before we can reach a convergent solution. Now let us look at this result. So when we assumed the block temperature as 500, we got to an outlet temperature of 583. But when it is increased to about 664, the outlet temperature reached 752. So in other words, we got to our requirement in both cases. Now let us look at these results. So we could see that we were able to heat ethyl benzene to the required outlet temperature as well as pressure. Now the question here is, after this simulation, which one of these options do you prefer and why? Do you think the option 1 is better compared to option 2 or vice versa, or both are same? So you need to use certain analysis in order to finalize or recommend one of these options. For example, how are you going to decide whether the first option is better or the second option is better? One way of looking at is what is the energy requirement for the first option, what is the energy requirement for the second option. And please check up which one is going to be higher or which one is going to be lower, are they equal. So to do this calculation, let me just look at individual results of these blocks. So in the case of pump, the amount of network required, let me put it in some units, kilowatts. You can see the amount of work required by this is 1.91451. Let me use a calculator. Type this value, 1.9145. This is the amount of work that is required by the pump in order to compress liquid ethyl benzene from 14.7 to 73.48. So in the same way, let us also look at what is the amount of energy required in the heater in order to heat this from 77 to 752. So once again, the netted duty, I'll convert it into kilowatts. So it is about 1460.53 plus 1460.53. So this is the total amount of energy required in order to bring in the required change of state with respect to ethyl benzene, about 1460.53. Please remember this. And now let us also try to look at what is the energy requirement in the second option. So in the case of second option, again in kilowatts, so the amount of heat required is about 1317.32. Similarly, in the case of a compressor, so you can see the network required again in kilowatts is about 145.168. This information here itself, 1460.53 is the previous one. So let me once again add. This is 145.168 plus what was the requirement in the heater, 1370.32 plus 317.3. Okay, 147. It is 145.168. 145.168 plus 1317.32 plus 1317. What about the total energy required in the first case. Probably you can see V3, this is 1460 plus 1.9. So what was this total? 1.9 plus 1460. You can calculate and you will be able to see that the energy requirement in both the options is exactly one and the same. Probably you might have done several problems in your thermodynamics course. According to the first law of thermodynamics, the energy required between the same two end states. For example, in the first option, we are changing the state of ethyl benzene from 77 degrees Fahrenheit, 14.7 to 752 and 73.48. And in the second option also, the initial state and final state are the same, but the path is different. You know, the total energy is not a path function, it is a point function. Because the initial and final states by both these paths are similar, the total energy required is going to be similar. So you will not be able to identify from the first law of thermodynamics or from the energy requirement which of these options is going to be better. However, you can think of utilizing second law of thermodynamics analysis to identify which of these options is recommended. In fact, you will be able to see, compared to analyzing these two options, generally one option is never considered compared to the other. Normally, the first option is always preferable compared to the second option. You can probably analyze and identify what exactly are the basic reasons why you can recommend first option over the second option. First law of thermodynamics may not be able to address this issue, but you need to use second law of thermodynamics analysis in order to come to a conclusion of recommending one of the better options among these two. So with this, I would like to stop this